Perfect. Thank you so much. And I promise that transition wasn't planned. It turns out Hashi just has a lot of great tools for security and a lot of great options. So we're going to jump right in. We've got a lot of ground to cover. This is a somewhat complex solution if you're seeing this for the first time. So I'm going to go through it all and also make sure that I share that all of the code is publicly available. And so if you do have any questions after the fact, you go and you try it, you run into any difficulties, don't hesitate to open up an issue or anything like that. As mentioned, my name is Jonathan Hurley. Good afternoon, good evening, good morning, wherever you're joining from or watching after the fact. I am a senior technical account manager with AWS, specializing in small to medium business and startups. So, sort of the folks who have for a long time been very much at the forefront of the containerization movement. So, a lot of great things coming out of both AWS and HashiCorp in tandem for those organizations. We are going to be looking at a zero trust mechanism for building, or I'm sorry, for requesting ephemeral IAM credentials. We'll be using HashiCorp Vault, and we'll be building entirely on top of Kubernetes, which we'll see as we go forward. I do want to start with this, just in case we run out of time. We're going to come back to this again at the end, but here is a link. You can find all of this on GitHub. Also, some of the code that I'll be showing is condensed a little bit, and some of it is quite frankly a little bit hard to read in order to fit on the slides. So all of the full examples are available here at GitHub. And like I said, if you do encounter any difficulties, you have questions, don't hesitate to open up an issue, and that will notify me immediately, and I can come back and jump into the discussion with you. Well, let's start by examining in a little bit more detail what we're going to do. We saw the title, but there were a lot of buzzwords in there, right? We're going to build an entire mechanism for interacting with AWS IAM roles anywhere, or IAM-RA. I'll abbreviate it at various times. And the vehicle that we're going to use for this is HashiCorp Vault. And HashiCorp Vault is going to play a couple of very pivotal roles in this. It is going to be running on top of Kubernetes. We'll see that in a second. And it's really going to be the central cog that makes everything else turn. What does it look like to build this? Well, on the left, you can see here, we have a Kubernetes cluster. In this case, as the icon indicates, it's running in Outpost, but this could be anything. This could be on bare metal. It could be on the Raspberry Pis that you may see in the background. Those are running Kubernetes. You could do this there. And we're running Vault there on that Kubernetes cluster. Over here on the right, we have an AWS environment. This could be a single account. You could create an AWS account exclusively for building this, or you could have tons of services there running. So what we need to do then is to integrate with IAM roles anywhere. You can see here on the right in our AWS account. The way that we do this is to establish a trust, and we build that trust within IAM roles anywhere, and we establish that we trust the Vault server. The way that we do that, as we'll see, is to take a certificate from the Vault server and use that, identify that in IAM roles anywhere as a trusted signing certificate from a trusted certificate authority. Once we establish that trust, we associate it to a specific IAM role. And this is going to be important. We're going to see this in code. So I'm not going to get too deep on that just yet, because I think it'll make a lot more sense when we see this in code. When a pod wants that role, or wants the credentials for that role, it reaches out to Vault. It generates a certificate on the fly that is signed by that trusted root certificate. And then it passes off its request to IAM roles anywhere. IAM roles anywhere, trusting the signing certificate, returns that IAM role directly to the pod. The pod can then use those credentials to perform whatever actions it intends. However, it's all wrapped by the security around the role itself, meaning, as we'll see in code, that the Vault role and policy establish credentials for the container, whether or not it can generate the signed certificate, whether it has those permissions. The trust is then established with IAM roles anywhere, and then the permissions of the role are what are adopted by those credentials. You may already be using AWS IAM roles with Kubernetes today by storing credentials as secrets, something like that. The big difference here is that these are fully ephemeral. These time out based on the settings of your IAM role temporary credential settings. So at best, these are short-lived, which is a really great use case for any services that need to interact with AWS intermittently in a very trusted fashion, right? We have multiple different spheres of trust here. Okay, that's what we're doing. But why would we want to do this? Well, first, we don't need to keep long-term credentials around anymore, right? We don't need those AWS IAM keys notifying us that they have to be rotated, that they're out of date. We don't need to worry about whether they've been leaked on the internet anymore because everything is now ephemeral. We're extending the AWS IAM trust space, that role space, outside of AWS. And we're doing that, going back to number one, in a fully temporary manner, in a fully ephemeral manner. And this is huge because it allows us to run Kubernetes clusters on-prem, at other clouds. Dirty little secret, it doesn't even have to be a Kubernetes cluster. You could do this on OpenShift. You could do this on bare metal, anywhere that you're running your Vault server. It allows us to then interface with those AWS services in a very safe and trusted manner. Vault Server is going to streamline this whole process for us by being both our trusted certificate authority and by being a secrets manager. We're going to see this in code coming up. And of course, the whole thing is zero trust. In addition to being a buzzword, it's a pretty good way to build things. So who is this solution really targeting? Well, anybody, any Kubernetes administrator, or like I said, kind of anybody at all, who needs to extend that IAM role structure outside of AWS. Probably you, if you're watching. When would we want to do this? Anytime. Anytime that we have that requirement, anytime that building a zero trust model for interacting with AWS resources adds value to our organization, this is a great solution. Of course, it helps if we're already running Vault Server, but we're going to see an implementation of it from scratch anyway. One important note. Even though you could do this within AWS, you could do this on EC2, you could do it on EKS, there are other structures to do sort of the same thing that exist within AWS. If you're familiar with IRSA or IAM roles for service accounts and the way that it interacts with EKS, that's basically what we're doing. So it is important that if you're doing this within AWS, although you could implement this model, there are other built-in solutions that may be a little bit easier and maybe a little bit of a lower lift. Where would we do this? Like we've talked about, this is anywhere outside of that AWS boundary. This could be on-prem, could be at other clouds. And it's not really important what the structure of the Kubernetes cluster itself is because this model is extensible. In this particular case, what we're going to see in code and what you'll see in the repository is that we put Vault in its own namespace. The reason that we do that is so that we can take advantage of constructs like network policies to be very careful with that namespace, right? There's a lot of trust that we're putting there by having it be both our signer, our secrets manager, and sort of our first line of defense from a policy perspective. And so we want to insulate that. So when I say that the structure of the Kubernetes cluster isn't terribly important, what I really mean is all of the other microservices, the consumers of this service, aren't particularly important, but you do want to make sure that you're always building Vault and running Vault in a very secure fashion. All right, let's get to the fun stuff. How? Well, I've been saying it all night, HashiCorp Vault. This is going to be the star of the show. Everything is going to lead back to HashiCorp Vault for us to make this whole thing work. And all of that begins with a Vault server. If you're already running Vault server on Kubernetes or you have in the past, this is going to look very familiar. We're just using the Helm chart, which is great news. We don't need a lot of customization. We don't need a lot of bells and whistles. HashiCorp has already packaged this up and made it available for us, and we're just going to install it. The next thing that we're going to do is a little bit of an add-on, and we're going to enable the Kubernetes Authentication module. The reason that we're going to do that is because that reduces the friction for our pods to have an authentication mechanism into Vault. Just like we don't want to have long-lived credentials in AWS IAM, we don't want to have long-lived credentials for our pods to authenticate to Vault. So in this case, what we'll be doing is extending a trust down to the service account attached to a pod. In fact, everything is going to center around that service account because all of our Vault policy permissions are going to point at that service account. This is just the foundation, though. You'll notice we're gathering some metadata here. We're getting a JOT, we're getting a signed certificate off of the cluster, and then we're going to pass it off to Vault itself. In this case, and this is all called out and documented in the repository, but we've already set up some type of connection to Vault, either through a port forwarding or on the Vault pod itself, what have you. So that's a little bit glossed over here for time. But once we've executed this final command and we've passed all of that metadata off to the Vault server, we're ready to go, and our pods can natively authenticate and receive appropriate credentials if there are appropriate credentials configured, which we're going to do next. We have to build a Vault role and policy. In this case, we're using IAM Anywhere as the name just for sort of a handy reference, especially if we're looking at audit logs after the fact. We want to know, hey, where did this request for these IAM credentials come from? Oh, it came from the role named IAM Anywhere. That makes sense, right? In real practice, you would have multiple of these roles because you would have multiple different applications that have multiple different permission requirements. But we simplified things a little bit here. You can see that we are using a shell variable called Vault Service Account. The reason for that is because there are a few pieces, and this is one of them, that it is absolutely critical that they tie all the way through this implementation. Another one that we'll see here coming up is the common name of the domain that we'll be signing. It's arbitrary. It doesn't matter what it is, but these have to be consistent across the entire implementation. Otherwise, you're going to end up with permissions issues, errors that are just a real bear to debug. So we do want to make sure that those are correct. You'll also notice here that we have tied this service account to specific namespaces. In this case, they're called front end and back end. Those, again, are arbitrary, but this is just one more example of how we can build this super strong zero trust model where we say, yeah, I trust this service account, but only if it's coming from these namespaces. Only in those scenarios do I allow it to even begin the process of requesting IAM credentials from IAM roles anywhere. The reason that we would do this is because we probably have our applications broken out into multiple namespaces in some sort of logical fashion. And so the applications that have requirements for AWS IAM credentials probably are either grouped together in a single or a few namespaces and probably have other components that interact with them that benefit from those credentials, right? So we want to make sure that we're always following least privilege here when we're doing the scoping and when we're allocating the permissions. Like I said, this is the really important part because this is what's going to tie those pieces, that service account, the namespaces, the permissions, the policies, all together. You'll notice that the policy is above. We've granted it a read-only policy. That's because we don't ever actually need to modify Vault for this to work. There are, of course, use cases where you may need to write secrets and secret data and other things that interact with Vault. But for our purposes exclusively, read-only is fine, so we definitely want to scope that way. We're going to take a quick right-hand turn and take a look at Vault Secrets Operator, or VSO. This is an optional component, but it does help out a little bit because we are going to have some pieces of metadata that need to be available as secrets to the pods. And VSO is a good vehicle for that because what happens is the secret remains in Vault, encrypted. It is protected by all of the permission policies and the roles and what have you. But VSO is a vehicle for the pod to get the secret contents in a secure fashion without passing through, the sort of availability layer of Kubernetes secrets that you may have encountered, depending on your security posture. This is another Really easy install thanks to HashiCorp. Right there in the repo, we add the repo, we install the package, we're off to the races. We do need to make a couple of additional configurations to get this off the ground. We're going to depend on a Vault connection, which tells VSO where to find the Vault server. In our case, it's running in the Vault namespace, and it's called Vault, so it's pretty easy. We have a Vault auth, which is going to tie back to a role and a permission that gives VSO the permission to read those secret contents and make them available. And those two things are combined then to create what's called a Vault static secret. We'll see that in a second. But you can see here just a quick manifest breakdown that builds that connection, that Vault connection, and that Vault auth. This is all there is to it. Of course, you'll notice we're still using that shell variable Vault service account because we've already built that trust there. In a real world implementation, you might have a totally different service account that is dedicated to VSO. There's nothing wrong with that. We're trying to keep things relatively simple since there are so many moving parts already. We're going to come back to VSO, by the way. I know I promised to look at Vault static secrets. We're not there yet. Now we need to build Vault as a certificate authority. And we're going to do that by enabling PKI. It's built in. It's already there because we've got the Vault server running. So yet again, thanks, Hashi. And we're going to set up a space that, in this case, is titled PKI AWS. You can call it anything that you want. But since this is a sort of interaction layer in front of AWS, I thought that this name made some sense. You'll notice that we're setting the max TTL to 8,760 hours, which is 365 days. Some quick mental math there. Now we need to generate a root certificate. This is a really important piece because recall, we're going to use this certificate to establish that trust. IAM Roles Anywhere is going to be given this root certificate and say, anything that is signed by this, you can consider a trusted request, right? So we execute this command. You'll notice we're using another shell variable here for the cert name. Again, this harkens back to that everything has to tie together. Otherwise, things are going to go sideways in a big hurry. But pretty straightforward as commands go. Once we've got that certificate in hand, you'll sort of take that and save it somewhere. We also need to set up a policy that's going to grant permissions to sign things through a request to Vault to our service account. As I said earlier, here's where we have that call out for that common name. You'll see it referenced a couple of different times. We've also, you'll note in that top policy that we are granting list and read on everything that's under PKI AWS. Again, that may not be appropriate for all implementations. Certainly make sure that you're scoping these permissions appropriately, especially if you have multiple different tiers or multiple tenants in your Kubernetes cluster that are going to be using Vault. You want to make sure that you don't inadvertently expose certificate data to the wrong consumer. And then the other two are all just about, like I said, signing and issuing those certificates, which will be very important coming up. We're also going to assign those to a role, right? So in this case, our role name is demo. We tie in our common name. And then in the second block, we are extending that, we are tying that in to the service account. This is a really important piece because this is how a pod with an associated service account can request a signed certificate from Vault. So all of these pieces now come together, and if we were to stop here, we could get signed certificates from Vault. That wouldn't quite get us where we're going though, because we still have to configure AWS IAM Roles Anywhere. Apologies in advance for the size of this icon. The picture is bigger in GitHub, and of course, if you go into your own AWS console, you'll see this full size. The big call out here is that since we are trusting Vault, which is running wherever it's running, it is external. So we'll select the external certificate bundle. That's the highlighted section sort of about 1/3 of the way down, we'll take our certificate bundle and we'll paste it into this freeform text box. And of course, it's AWS, so tagging is recommended. There's a whole notification section. There's a whole additional security configuration section. Explore those. I definitely recommend being familiar with them, but you don't have to have them. And especially if you're just testing this out, trying to get a sense of it, there's a whole lot going on there that can certainly lead you astray as well. So we'll keep things simple today. The next step, as we saw earlier in the animation, is to create an IAM Roles Anywhere profile. And the profile is what's going to tell IAM Roles Anywhere that for the certificate we just uploaded, it's okay to give out credentials for this role, right? This is the way that Vault, as a certificate signing authority, is trusted all the way through to the IAM role credentials. So this is a really important piece. This is another area where we're sort of glossing over the tagging, the inline policies, all of that, because you don't really need that. There is one additional component on the role side. It's not shown here, but it is mentioned in the repository, which is that IAM Roles Anywhere has to be trusted by the IAM role itself for an STS assume. If you do a lot of work in AWS IAM, you'll be very familiar with what that looks like. Very standard approach there. Okay, all of our pieces are in place. So what does this actually look like when we do it? Well, first things first, we're going to pop some values into Vault itself. These are just standard Vault secrets. If you've been working with Vault as a secrets engine, this is going to look very old hat. What we need to capture is the ARN of the IAM Roles Anywhere profile that we just created, the ARN of the anchor, which is where we uploaded that certificate. What it generates is called an anchor, and the ARN of the role that we will eventually adopt. So as you can imagine, there could be multiple sets of these, right? But just like we saw with the service account, the common name, this is one of those areas where if you've uploaded multiple certificates and you can't remember which one goes with which role, for example, or you can't remember which one goes with what section in Vault or service account or what have you, these have to be correct. The result of them being incorrect is that you just get a permissions error, right? You can't get those certificates, but that's annoying. And we want to avoid that if we can. So it's best to make sure that all of these tie all the way through. The next thing that we'll do is a little bit of Kubernetes setup. This is where we see that Vault static secret. As I said, the VSO component and the Vault static secret as a result is an optional component, but look at how nice that is. You just reference the secret that you created. So this one in particular references the anchor, and that's pretty much it. I mean, yeah, you reference the Vault auth that we created earlier. You tie it to a namespace and all of that, but this is pretty handy, right? If you've dealt with Vault secrets not using the VSO, you've probably had an experience where you may be pulling your head out or your hair out, sorry, trying to remember like where you put a secret or what have you. So this makes it very convenient. This makes these very portable, and especially gives us a really convenient name, a reference in Kubernetes, so that we can see, show me all of the static secrets that are available in this namespace. If the only thing we're doing is IAM Roles Anywhere, then that could easily be, a list of all of the roles that could be adopted in that namespace, something like that. So this can be a huge convenience factor. This is what a pod looks like, sort of. We have had to shrink it down a little bit, so I do apologize for the eye chart a little bit here. But you'll notice that we're setting up the environment. We're telling the pod where to find Vault, which in this case is vault.vault.service.cluster.local on the default port of 8200. Doesn't get much more easier than that. The Vault role, which is actually going to correspond to our service account in this case, but it doesn't have to, right? These could be different strings, but it can get very confusing to try to remember, is that the Vault role? Is it the IAM role? Is it the Kubernetes service account? So whatever makes the most sense for your organization to make sense of all of that certainly works. We also have a reference to the image, which in this case is stored in ECR. Certainly not a requirement, but it is convenient. And a reference to our Vault static secret that we created earlier. And there are our service accounts. When we actually launch this pod, then we have an opportunity to actually interact with IAM roles anywhere. And this is where things get sort of very abbreviated. The Python script that you see here, the gencert.py, that is included in full text in the repository. I tried to include it on a slide and it just did not fit. But basically what it does is to use the Vault module for Python to interact with the Vault server and request a signed certificate. And then that certificate, which you'll notice here in the bottom, cert.pem, private.pem, chain.pem, those are the pieces that you need, right? Those get handed off to the AWS signing helper, which is publicly available from AWS. And you'll notice we're also referencing some shell variables. Those can be set up in the pod as environment variables. They could be in secrets. They could be almost anywhere, right? But we're referencing there the trust ARN, the profile ARN, and the role ARN. And this is another area where these have to match, these have to tie, because IAM roles anywhere is going to get this request from this signing helper script. And it's going to say, okay, I have someone passing me a certificate. They're passing it to this anchor. They're saying that they should have access to this profile. And they're saying that that profile should be linked to this IAM role. And if anything is wrong there, you get a permission error. So it's very, very important that that's all correct. But when that all lines up correctly, what you get is what you're probably familiar with from setting up any normal AWS account. You get a secret key, and you get, you get an access key and a secret key, and you can use those until they expire. In fact, in the repository, I have an example of doing this as a sidecar pattern. And so these steps run just in a standalone container, but as an init container. And then they hand off just those credentials to the application container. And what that means is that from a developer experience standpoint, they don't need to know how any of this works. From their perspective, they start up an application, they can immediately execute the AWS CLI or use a Boto 3 or whatever the appropriate vehicle is to interact with AWS in their code. And those credentials are just there and they're just valid. They're just correct. And so it can be a very, very low friction experience for the developers. But as we've seen, so many different gates where we can build very highly tuned zero trust models. So a really great way for us to be very prescriptive about exactly what that developer application can do in AWS without really having them have any ownership of how that all gets set up. Furthermore, we have opportunities for all kinds of things like retiring credentials, right? We deprecate an application or we move to a version that changes the way it does things or what have you. All of those same security gates that we've been working so hard to set up throughout this session give us opportunities to immediately end that access for that application. So that's going to be great for our security team, for our audit teams. Of course, all of this is available for audit as well through AWS CloudTrail. These are just normal IAM requests, and it is all auditable at 100%. Vault, of course, if you're not already familiar, Vault offers a fantastic way to audit requests against Vault. So you have a complete end-to-end chain of custody for your credentials as well. One more look at that link to GitHub. Feel free, like I said, go take a look at the source, full examples there, opportunities to open issues, ask questions, anything like that. And that will do it for me. Again, my name is Jonathan Hurley. It has been a pleasure, guys. Thank you all for joining, and I will see you next time.